Figure 1 shows an experimental setup of hair separators used in a school laboratory to measure the relative density of a liquid. In the figure, water and liquid are labeled as A and B respectively. Part A1 give an approximate value of the diameter in centimeters of the tube in both arms in hair separators normally used in school laboratory. If you are using it, you have used it, you know that approximate diameter is about 1 centimeter. At the examination, they have given marks for all values between 0.4 centimeters and 1 centimeter. Then part 2, name the measuring instrument that is not shown in the figure given but needed for this experiment. They have not given ruler, they are using meter ruler to measure the corresponding liquid heights. Then part 3, state clearly how you would establish and maintain water and liquid column in arms of the hair separators. In the hair separators, there is a rubber tube. In this part, there is a rubber tube and we are using a clip. First of all, we have to open the clip and then we have to open the clip and then we have to suck air inside the column. And after getting a suitable height for the water column and liquid column, again we have to close the rubber tube by using the clip. Then we can write, open the clip and suck the air column. Inside the tube. And finally, we have to close the clip. We have to close the upper end of rubber tube properly by using the clip. Then part 4, what is the special advantage of this method over the U-tube method? We can use this method for mixable fluids. We can use this method with mixable fluids. But we know that when using U-tube experiment, we are using only fluids which are not mixing each other. Then part B, in order to determine the surface tension as well as the density of a liquid, a student has modified the hair separators by replacing both arms with identical capillary tubes of internal radius r as shown in the figure 2. Part 1, let P0 be the pressure of air above the water and liquid meniscus, HW, HL be the heights of the columns, dW, dL be the densities and TW, TL be the surface tension of water and liquid respectively. If PW and PL are the pressure at point W and L respectively, write down expression for PW, PL in terms of relevant parameters. Assume that the contact angle of water and liquid gas are 0. Now they have given a figure like this. This beaker is water, this one liquid, and they have given corresponding water height HW and corresponding liquid height HL. Now we have to consider the surface tension. Therefore, when writing pressure at this W point, PW, we can write pressure inside the tube, this region P0, and when coming through the meniscus, we have to subtract 2 TW over R. It is the pressure difference between difference of meniscus. And again we have to consider when coming from inside to outside. Inside means this curved, we have to consider this side is inside, this side is outside. Pressure difference between this side and this side is 2T over R, but we have to subtract it because of inside pressure is greater than outside pressure. And when coming through the water column, we have to add HW, DW, G. Then we can write pressure at this point, it is point L. We can write PL. Again P0, when coming through the meniscus, we have to subtract 2 TL over R plus HL, DL, G. Right. Now part 2, hence derive an expression for HW in terms of HL, DW, DL, TW, TL, R and G in the form Y equals mx plus C. We can consider that pressure at this W point should be equals to pressure at L point because of both are equal to atmospheric pressure. Outside pressure is atmospheric pressure according to Pascal principle. We know that pressure in this point should be equals to pressure in this point. There is the same level and same liquid. Then we can write pressure at W should be equals to pressure at L. We can write pressure at W P0 minus 2T W divided by R plus HW dWg should be equals to pressure at L P0. This one should be P0, it is inside pressure, minus 2T L over R plus HL DL G. Now we can cancel out P0 and P0. We have to write the equation in the form Y equals mx plus C. We have to change the length of liquid column. It means HL. Therefore, we have to get HL to the x-axis and we have to measure HW to the y-axis. Then we can write HW dWg equals dLg HL minus 2T over R. We can bring this one to the right hand side plus 2T W over R. Then we can divide all terms by dWg. When dividing this one, we can write dWg. Then we can cancel out G and G, dW, HW equals dL divided by dW, HL minus, I will write this one, 1 over dWg times 2T L over R plus 2T W over R. Now it is in the form Y equals mx minus C. It is the answer for B part 2. This one is B part 1. Then part 3, if you draw the graph of HW versus HL, if you know the values of dW, TW and R and G, what quantity should you extract from the graph to determine T1 and TL and DL? When finding TL, we have to get intercept from the graph. Then we can write to find TL, we have to find intercept of the graph. When finding DL, we can find DL value by using gradient. Then when finding DL, we have to get gradient of the graph. Then part 4, why is it always suitable to have a height of water and liquid column as large possible? When using a large water column and liquid column, we can maintain a low percentage error. Then we can get to maintain a small percentage error.